only 8 of us. Okay. Are you supposed to be in a class somewhere? Okay. Like, did somebody listen to St. Pierre? Or am I getting in trouble? Okay, here we go. All right, I'll run through these really quickly, but we're not, until we start using them, they're not going to make a lot of sense. You with me so far here? Okay, so if this is called the identity function, because your function is x. It's just x. Y equals x. And here, that's your function is x. So as x approaches a, well, if this just means my function would be y equals x. So if x is approaching 2, what's my y doing? It's approaching 2. Because they're the same thing. Your x and your y are doing the exact same thing. So this is called the identity function. Right? So because y and x are equal, so if x is approaching 2, your function is going to be approaching 2. Easy, right? The basic one. Okay, constant function. So a constant function would be y equals 3. So it doesn't matter what x is approaching. What's my y? 3. So my limit of my function is 3. Not hard for a little bit. Okay, so now this is, if I have a function and it's multiplied by k, and k is constant. The letter k is a constant. All right, so if my function is multiplied by k, all that means is I can pull that k out and take my limit and multiply it. Okay, so we'll go through later and see that. So if the function is multiplied by k, the limit is also multiplied by that k. It's pulled out. And these are pretty straightforward. These kind of remind me of log laws, kind of. No, not really, because we multiply logs, stuff like that. But if your f of x and g of x function are added together, you can bust them apart and do the limit of 1 and then the limit of 2. And the same thing with the difference. Same thing with the product, and same thing with the quotient. Okay? It's almost like your argument can be busted into these two, and I guess that's like a log law, right? That's similar to your log laws. This isn't, because this would have been, but this one's similar to a log law. This one, if your function is to the exponent, your limit's to the exponent. Pretty straightforward. These are all in your formula sheet. Like I said, they're not going to make much sense to you until we actually like do stuff. There's only 5 pages in the space. All right. Example 1. We're asking to evaluate. So my function has an exponent on it. So what theorem am I going to use? What?
We can change it.
No, it's okay. Which one is it? Oh, okay. Here. We'll hop back here. Okay, we'll hop back and forth. No, we have. And this one's nice and easy. This is nice and easy. Let's start with easy. Start with easy. Yeah. That's what do you guys have this one? Yeah. Okay. All right. Looking at hard. Okay. It has an exponent. So what theorem am I going to use? The power theorem. So this tells me that I'm going to use the power theorem. Okay. The power theorem says I'm going to flip my page already. I'm going to evaluate the limit of just the function. So as x approaches 3, right? So I can write this as that. These two things are the same. Now we're gonna evaluate. So we're gonna keep going. So what is this? When there's just a single x there, that's the identity theorem. So what's the limit of the identity theorem when x approaches 3? 3. Guess with me? Right? Because this is y equals x. That's my equation here. So if x is 3, the limit is also 3.
Oh.
You can't have equal signs. How come? Right, it's an expression. We haven't done anything, we just evaluated it down, right? Okay, so we use the power theorem and we use the identity theorem. Nothing rocket science so far? Okay, so finding the example on the page is the part. Okay. This is a constant, so what's the limit? And I'm going to use the constant theorem. There's no x's, there's no nothing, so it doesn't matter what x is doing. So for the constant theorem, y is 5. Doesn't matter what x is doing. Okay, brackets. Super duper important. Okay, you ready for this? You ready for this? Okay, so this one says that everything here is in the brackets. This one says, I'm taking the limit of this, and then I'm going to add a random x onto it. So these are two totally different things. If I expand this side, so this would be limit as x approaches 1, so this would be x plus 2 times x plus 2 plus x. Just doing some math here. I'm assuming you're on multiplying as well.
Yeah.
So here's the thing, is if you have a limit and then everything after it is that function. So if we were to evaluate this, we're just going to do some direct substitution for this equation. Would there be an asymptote or any indeterminates for this one? No, because we don't have a denominator, right? This is just going to be your standard old parabola. So what's the y value doing when x is 1? What's the y value? So it's just x is 1. What's 1? Yeah, the value. Okay, all right, yeah. No, see? You guys know how I got 10? Yeah, maybe the x squared is important. So direct substitution, if I put 1 in here, that's 1, 5, and 4, so the limit is 10. And that's just a point on that parabolic curve, right? But it happens to also be the limit as well. So if I do this one, this is just going to be the limit as x approaches 1 of x squared plus 4x plus 4. And then I've got a random x over here. The limit is only applied to this bracket. It's not applied to that. It's like, take the limit of this and then slap that on at the end. So if I evaluate the limit of this function when x is 1, what's the value of this when x is 1? Now it's 9. So this is 9. Nihal is just working ahead. And then this is just this random plus the x. So I'm not taking the limit of it. The limit of this function is 9. But to simplify this, if I were to simplify this, this limit is 9, and then I can't ignore that x, so I gotta bring it down. But the limit is only of this function. Everybody good with that? So brackets make a huge difference?
Yeah.
Okay, so it's everything after the word limit has to be in brackets to be evaluated. Okay. We're going to verify that the theorem is this. This is the constant times a function theorem. Works. Okay. So we'll do the left-hand side first. Oh, look, it's like proofs. Your favorite chapter in pre-calc. 6. I really love it. I think that's why I like it. It's like this puzzle that you have to solve. Okay, so is there an asymptote or an indeterminate with this one? No. So we know that the point is going to exist on that linear function. So if x is going to 3, if I substitute 3 in here, 25, right? Does that make sense? So it's just a point on the line. As x is approaching 3, the y values are approaching 25. Okay, so now let's do our right-hand side. So this is the constant times function. So you see how there was a 5 in here? So they're saying that if I pull this 5 and put it on the outside, I should get the exact same thing. So 5 on the outside times by the limit as x approaches 3 of x plus 2. So we're going to evaluate this first. So what's that? 5, because we're going to put 3 into the x, and that's going to give us 5. And we're going to have 5, that's 5. That also gives us 25.
So for that one, the
limit of this function is 5, but times by that constant is also 25. So the limit with the 5 of these limits gives me 25.
okay.
Does that make sense?
Yeah.
Because we put that 5 in here. So it doesn't matter if it's inside or if it's outside, you should get the same thing. Okay, we're going to verify that this one is correct. Okay, so big brackets, so I'm going to combine like terms. So the left-hand side is going to be the limit as x approaches 3 of 4x plus 1. Right? 4x plus 1. And then I'm going to do direct substitution. I'm going to, because again, there's no indeterminate, there's no denominator. So I'm going to do direct substitution into here. So the limit of this is going to be 13. 12 plus 1. Okay. So this is saying that whether I add them inside the brackets or whether I evaluate them separately, I should get the exact same thing. So limit as x approaches 3 plus the limit as x approaches 3. So again, we're just going to do direct substitution here. This portion of the limit is going to add to 5 hopefully, and this one's going to be 8. 5 plus 8 also gives me the 13.
If the second leg had a x approaches 4,
You wouldn't do that because then it wouldn't be part of the theorem. The thing with the theorem is that this gets transferred to both here and here.
okay, so
They have to be the exact same. It's kind of like your logarithms have to have the same thing, right? Yeah. X plus 3x gives me 4x, and 2 minus 1 gives me 1. So No, so like the logarithms you would multiply. Well, limits theorems are similar to log rules. They're not exactly the same, but you same thing. Like your x's have to approach the same number, just like your logarithms have to have the same base. Right? So I'm trying to relate to stuff we've already done. It's not perfect, but we get the idea. Okay, so this one's a multiply one, same sort of thing. The idea is when you get a really complex log that has all the same like x approaching, the idea is that you can simplify it into one, I said log, not limit. You can simplify it into one limit and make it a little bit nicer to deal with. The left-hand side, hey, do you guys think that it would be easier for this one to do direct substitution in and then multiply? Like my gut instinct was to just go and multiply my. Is that what you did? No, like, so this would be 3x squared minus x plus 6x. I think direct substitution would be easier. How does that make you guys feel? You guys good with that? So 5 times 8. So my limit would be 40, because that would be a constant function, right? Ooh, look at us, skipping steps. Okay, so that's kind of what we did here. We're again, if we just do direct substitution in, we're going to have 8. Sorry, we're going to have 5 times 8, and we're going to be at 40 again. Because if I do direct substitution into here, that will give me the 5. Direct substitution, that will give me the 8, and that will give me my 40. No, you totally can do that. Okay. Yep. You've done something wrong. This is a limit. This is a theorem. So somebody somewhere has spent a ton of time proving this is always true. It's like the Pythagorean theorem. It's like if your a squared plus your b squared doesn't equal your c squared, it ain't the theorem's fault, right? One of those things, right? Like, it's just bad. Okay, this one. Okay, am I going to have an indeterminate here if I direct substitute that 3 in? No, because I won't have a 0 on the bottom. So I'm good, right? Like as long as I don't have 0 on the bottom, I don't have an asymptote. For this particular, I'm looking at x approaching. Oh yeah. Well, you will. You did that yesterday, right? Left-hand side, so limit, you're just going to direct substitute. So now it's like, I may have jumped the gun because it was something I'm supposed to show you later. Okay. So this would be the limit as x approaches 3 of 5 over 8. Notice there's no x's in it, so that is a constant theorem. So my limit is 5/8. And again, if you separate them, you're going to get the exact same thing. So the right-hand side, I'm going to have limit as x approaches 3. That one would be 5. And limit as x approaches 3. It's going to be 8 if I do the direct substitution. Again, constant function, so that's going to be 5. That's supposed to be a 5 over 8. So nothing too terrible, right? See, calculus is way easier than pre-cal. Like, let's do in pre-cal, you were trying. Right? Oh, transformation, nobody was trying. Oh, Sinusoidal little functions are a little bit difficult. Okay. All right. So we've been talking about direct substitution. I kind of ruined the fun. I just want to show you the difference between the two. You guys have a cubed on yours, right?
Yeah.
Okay, good. Okay, so you can do it using limit theorems, or you can do it using direct substitution. So I could evaluate as limit as x approaches 2 of 2x cubed minus limit as x approaches 2 of 3x plus limit as x approaches 2 of 5. Okay, so that's the limit theorem, like, and I'm not even done yet, because this one has a constant and a power. Okay. So that one would be, the constant gets pulled out in front, so 2 limit x approaches 2 of x, and that's all cubed. Oh, never mind, that's not all cubed. Yeah, I need to erase something though. It's only the x. I almost said it with my graph. Oh, there you go. So my 2 got pulled out and the limit got cubed. Good. Okay, so for this one, the constant gets pulled out. That's a big x, which is 2. And then this one is what it is. Okay, so now this breaks down, like if you can do it this way, you can see everything's a lot easier to do. This is your identity theorem. So if x is approaching 2, y is 2, right? So it would be 2 times 2 cubed. So that would be 2 to the 4, so that would be 16. And this is an identity again, so this would be 3 times 2. And this one's just a constant, so it's plus 5, so this would be minus 6 plus 5. So the answer would be 15. So that's if I broke it apart using theorems. Okay. But you know there's a different world out there. It's called direct substitution. And it is a glorious world because it goes way faster. So if you direct substitute, oh, did you guys do that? Sorry. So that's one way to do it with limit theorems. Obviously a lot more complicated than it needs to be. If you do direct substitution for this one, I don't know where it is. You're going to direct substitute into it. So the limit as x approaches 2 to x cubed. We're going to direct substitute into it, so we'd be taking the limit as x approaches 2 of 2 times 2 cubed minus 3 times 2 plus 5, and that would give me the limit would be 15 because it's a constant. So direct substitution to me is way easier. And I would be perfectly happy if you went from this line to that line and missed these 2 steps in there. I'm just putting them to make it look impressive. It really isn't. Direct substitution, when you can use it, do use it. It's so much easier. Any questions, Kale? Okay. I want you to do this one. I'm going to hit pause. Dale, you do this. I want you guys to bust this out using limit theorems. I want you to fully break it out like I did. One more theorem that I was supposed to use, but I running out of room, so I might not use it.
So we have to.
This one, we take the 3 out.
I just did that like.
You did it all in one step?
Yeah.
Perfect, let me do that. My 3 goes over here, and my X goes here. Beautiful, yeah. Because you don't, maybe you just, you've only been dividing those two.
Yeah.
Okay, so the idea of getting it down to a constant function or an identity function is that it's going to be quick, right? So we have 3 times 2 plus 5 over 2 minus 1. So 6 plus 5 is 11, 11 over 1 is 11. Okay, but that's an awful lot of work, but there's benefits to doing it because there's going to be a lot of stuff that doesn't work with direct substitution. So, okay, so now if I do direct substitution, this is pretty easy. Well, it's easier if my pen works. It's a lot less easy if it doesn't. Way easier. Direct substitution, way easier. If it works. Okay. Let me tell you. So we're going to do, if we get into a situation like that, we're going to go back to our table of values because this would be an NPV. So as x approaches 2, that would give me a denominator of 0. And so then we go back to our table of values and pick those numbers from the left-hand side to the right-hand side to make a decision on what y is doing at the time of the gas. Anything else I'm supposed to you? Does that make sense? Why it might not work during substitution? Yes. NPV. I was saying the same thing. Right, so if I have a 0 for a denominator, I can't evaluate it. Like if I say 3 divided by 0, you do that in your calculator, it's going to give you an error. That doesn't answer my question. There will always be a limit, even if there is no limit. Right, we discovered that yesterday. You can have limits even when the graph doesn't exist at that point. You just use your table at that point. All right.